Hello everyone. In this talk, I will be presenting our paper, Improving Unsupervised Domain Adaptation, a Pseudo-Candidate Set Approach. Domain adaptation refers to the problem setting when there is a domain shift between the source domain and the target domain. In this work, we focus on unsupervised domain adaptation UDA. In a typical UDA setting, we have a labeled source domain and an unlabeled target domain during training time. Hence, the goal of UDA is to adapt to this unlabeled target domain during inference time. In recent years, two prominent categories of methods have emerged to address the UDA problem, namely adversarial learning and self training. Apart from these, hybrid approaches that combine these two have also been published. Despite the existing efforts, we recognize an opportunity to further enhance the target performance by analyzing the patterns in the predictions of the trained UDA models. To understand this further, let us focus on the second row of the image as shown. The second row consists of UDA model predictions, and as observed, these predictions are ambiguous. Further, we observe that this ambiguity is not evenly distributed across all the classes, but it is focused on certain subset of classes. Hence, to tackle this ambiguity, we propose unsupervised domain adaptation refinement using pseudo-candidate sets technique. The following are the key contributions of our work. We introduce the concept of a pseudo-candidate set for the first time in UDA. We propose a novel refinement technique UDPCS by leveraging the pseudo-candidate sets. We study the proposed method by conducting extensive experiments and observing consistent gains. These are the key important terminologies that are used in this presentation. We will first talk about the UDPCS methodology and then we will illustrate it with the help of a toy example. As discussed, UDPCS is built on any off-the-shelf UDA method. Hence, the model hatch is first trained using a standard UDA technique. Later, this trained UDA model is used to generate the pseudo-candidate set for target data as shown in equation 1. We will next define a label confidence vector W as shown in equation 2, where each element in W signifies the confidence that has been assigned to a particular class J. To refine the predictions, UDPCS is trained using two loss functions defined as follows. The candidate loss, as shown in equation 3, consists of a KL divergence between the vector W and the model predictions. As further observed from equation 3, the candidate loss is only applied on those samples where the maximum predicted probability is less than a threshold gamma. We next define the non-candidate loss as shown in equation 4, where this loss is used to penalize the model whenever it makes predictions on the classes outside the pseudo-candidate set. The total loss of UDPCS is as shown in equation 5, which is a weighted combination of the two losses. Next, we will talk a bit further about the confidence vector W. Equation 6 shows that the vector W has been initialized uniformly using the pseudo-candidate set Z. Equation 7 shows that this vector W is iteratively updated with the help of model predictions. Let us now illustrate the working of the UDPCS method with the help of a simple toy example. For this example, let us consider a 5-class classification problem and 5 target samples S1 to S5. We will demonstrate a single step after the UDA training. As discussed, after the UDA training, the first step is to create a pseudo-candidate set Z from the UDA model predictions. We then initialize the normalized label confidence vector W. With the help of this vector and the pseudo-candidate set, we then update the model parameters of the refined model. In the next time step, this updated model then generates its predictions on the target data, which is then used to get the disambiguated vector W. In this way, we iteratively refine the model predictions with the help of UDPCS technique. This is the algorithm of our UDPCS method, which illustrates the same working as discussed previously. To evaluate our UDPCS method, we conduct experiments on 3 different benchmark datasets, WizDA, DomainNet, and OfficeHome. To further assess the effectiveness, we conduct experiments on a bunch of different UDA baselines. These are the results that we observe. In table 1, we show the results on the WizDA datasets, and on the rightmost column we can see that with the help of our method we observe consistent gains across different baselines. On an average, we gain 2%. For DomainNet also we observe these consistent gains with an average gains of 1.7%. Similarly, we observe consistent gains on OfficeHome dataset when using our UDPCS method. We also conduct several empirical analysis and ablation studies. As shown in Table 5, we assess the impact of different UDPCS components. In Table 5, we show the complexity analysis in terms of the trade-off between time and accuracy. We also show a bunch of analysis of different hyperparameters used in UDPCS method. Thank you all for listening. In case of any queries, please contact the authors and please do visit our website. Thank you.